that you can express that as a unitary, but this unitary can be also a composition of product of smaller unitaries that acts on possibly different subspaces. This example here, in Penny Lane, you see that you can define a device. A device is either quantum hardware or a classical simulator. After that, you define your circuit. This circuit represents your quantum function. You can take some parameters. And you see that you define those little unitaries that are here, the rotation y and the CNOT gate. You can represent that on the right. You see that you have two Ry, each on 1 qubit, so the qubit 0 and the qubit 1. The CNOT is applied on the 2 qubits. After that, you have like to get an actual result, so you have to do a measurement. So we take the expectation value of the observable Z, and that's what you see on the right for the drawings. So now we want to differentiate those quantum functions. So if you take the definition that we had 2 pages ago, we can define a variational quantum function as this expectation value of this observable O. You see that you have like the unitary evolution on the right and the dagger on the left. So you want to differentiate that. That's great. You can take the Nabla operator, and you see that the state actually on the right and on the left do not depend on the parameter theta. So you can apply it on the transformation of the observable, and we call that M. So now that's great, and you have like to actually calculate your M. And they came up with adjoint differentiation some years ago, and that's very efficient on actual simulators, because in simulators you have access to the state, which you don't have access on real hardware. So adjoint differentiation is used when you have an efficient simulator to get those derivatives. So if you take the derivative of the measurement of your observable O, you see that you can use the product rule to apply it one time on the left plus the one time on the right. Given that the rule for complex numbers, you can see that it's 2 times the real part of only having the differentiation on the right. After that, you see that you can, with this expression, you can separate it in 2 parts. So you have the Bi, that is the bra on the left side, that takes everything from U0 to UN, going through O, and then going back to I plus 1. Then after that, you have Ky, that is everything that is on the right of your derivative. And you see that finally the derivative here of your measurement is only twice the real part of the overlap of the 2 states. And that's very practical now because you can calculate those states recursively. The only thing that you need to know is the differentiation of your unitary UI, which is usually simple to get because it's a gate that is applied on 1 or 2 qubits. So that's great. We have something to calculate differentiation of quantum function, but that's only for simulators. Now, they came with a parameter shift rule that is for quantum hardware. So you have like 2 main papers that introduced that in 2018. I will not go in details, but the intuition here is that we can express the derivative of this transform observable O as a linear combination of the shift of the when you shift the parameter. So you see that you can shift it by s and minus s. You get the results of those two quantum execution, and that gives you the derivative. The good thing here is that it's an exact method. This is not, like, you could think it's related to finite differences, but it's not. And you can, with two quantum execution, you can get the results for your derivative. If you take the example for gates that are x, y, and z generated, you see that the shift is pi over 2 and minus pi over 2. So now that we have a way to differentiate quantum functions, we would like to integrate that in automatic differentiation. So what you can do is simply that for your forward pass you execute the quantum function, and for the backward pass you have like to register the custom VJP, for example. And I've shown you the rule to get the Jacobian. You can multiply that with the tangents or the contingents, and you can register custom gradients. So that's what we do in PennyLane. So PennyLane is the Python layer of the library, and you see on the left you have a circuit, a quantum function with two rotations, and you see that you can integrate that in a cost function that is using sinus and absolute value, and you can, thanks to automatic differentiation, get the gradient of the whole thing. We have support for AutoGrad, TensorFlow, PyTorch, and JAX. But everything is not perfect. The current issue with the Python layer is that, okay, you don't have a direct access to your quantum computer, so you will use a REST API to make a call, to send to the cloud your quantum function. Then it will be in a queue. You will wait a bit. It will be executed. Then you receive it again, and you see that it makes a lot of latency between the classical and the quantum components, and we would like to reduce that. Also, as the hardware and the algorithm they scale up, the Python classical or pre-processing or post-processing can also become bottlenecks. And there are increasing requests for heterogeneous devices. I didn't talk about that, but potentially, for example, for error correction, you would like to do the decoding on the GPU, and if you don't have direct access to your quantum computer, or you don't have a representation of your whole quantum classical program, make things very complicated. So we have support for JAX cheat. So that means that we can cheat those quantum classical functions. That's great. You just add JAX cheat as a decorator to your quantum node, for example, here, and you benefit from the compilation, and you go through XLA. It's great, but the only problem here is that the whole quantum part is just a Python callback. So we see that it's also not optimal. But we were inspired by that, and that's why we introduced Catalyst, because we want to be able to run things on hardware and simulators. We want also to be able to have a classical compile code that integrates the classical part and the quantum part, and we want to be able to run this whole program as a collocated hardware. So we want to take advantage of hybrid compilation. And that's what we introduced Catalyst. That's our JIT compiler, hybrid JIT compiler in PennyLane. You see that it's just a simple decorator that you use on your quantum nodes, or more generally on quantum classical functions. So that's great, because now you compile once, and after that, all the further execution will be run faster. You see on the left here the QGIT decorator as a autograph is equal to true. It allows user to keep the Python interface for loops, conditionals, and while loops, because you don't have to write those loops that were written in Catalyst. Autograph will just identify those loops, make them functional, and call the Catalyst equivalent that lowers down to structure control flow in MLIR. To give you an overview of what is happening under the hood, so you have the Python layer. We use JAX to trace the quantum classical function. We have register primitives for the quantum part and for the hybrid functions like the for loop, the while, and the conditional. We all register that as primitives. You can create a JAXPR that contains classical and quantum code. So that's the first step. Capture the quantum program, represent it as a JAXPR. The second part is to lower everything down to MLIR. So we use also the function from JAX to lower to MLIR, but plus our custom lowering for everything that is quantum, gradients. We also added recently error mitigation, dialects. So all of those are dialects in MLIR. After that, we apply some quantum classical optimization in MLIR. We lower the dialects to enzyme calls, and that will be the last part of the talk, is how we integrated enzyme to drive the automatic differentiation. So we go down to LLVM IR, plus every quantum call is following the QIR specification. It's just a specification to write LLVM function, and then we implement those calls in a quantum runtime, and that we linked against at the end. And you see that the automatic differentiation will happen at the LLVM level by calling enzyme autodiff. So I want to give you a quick example here. That's kind of a side effect of our work, is that you can differentiate any classical Python code and also most of JAX code. So you see we leverage also the front end from JAX, because we can use PyTrees flattened and unflattened, so you can differentiate through dictionaries, lists, tuples, anything that respect the PyTree specification. So you see here you have just a simple JAX function that use sum, get a dictionary with data and weights, that also use sinus, and you just apply the QGIT decorator instead of using XLA. It will lowers down to MLIR, then LLVM, but like the standard dialect, not XLA, and it will use enzyme for the differentiation, and you see that you get the same results. The first step of the lowering is, as I said previously, lower to the JAXPR. So you see you have the JAXPR on the right. There is like a gradient primitive that we have registered that contains all the necessary parameter and the JAXPR of the differentiated function. You see that after that you go to MLIR. We have a gradient dialect. In this gradient dialect we have a gradient operation that will be lowered down to an enzyme call. Here you also see the function to differentiate that was registered, that was lowered down in MLIR. And then after that, as I said, we have those multiple step gradient lowering to the LLVM dialect in MLIR. And finally, after that, you have this conversion from the LLVM dialect to LLVM IR. And we apply O2, and after that, we finally call enzyme. and it gives you the binaries for your classical quantum program. In that case, it was just classical, but yeah. Here is another example. There is a quantum program with also some classical preprocessing inside. I have used autograph to make things simple and that we don't have to use the catalyst for loop and the conditional from catalyst. So you see that you have quantum operation, you have a for loop, and then you have a conditional. So the structure of your quantum circuit depends on classical parameters. And we can take the differentiations through that. If we just look at the quantum program here, you see that first we have a quantum device that represents the hardware or the simulator. We capture the for loop in the Jaxper, the conditional in the Jaxper as well. We keep tight representation in penny lane, for example. Something like that will unroll the quantum program. So you will just have like an exploding representation for your quantum code. After that, you lower to MLIR once again, and you see that we use the structure control flow dialect for the for loop. We use the also the structure control flow dialect for the conditional, and you see you have quantum operation a bit everywhere, and that's not an issue. So we have a compact representation for hybrid programs. That's great. I've shown you an example with differentiation of a classical function, an example with the quantum program. But what you can do now is just use that on hybrid workflows. So you can also use Jax-opt gradient descent on a cost function that was defined as the gradient of a quantum circuit. Yeah, so now for the last part, I'll just explain a bit more like what we have done to integrate enzyme for like driving the automatic differentiation. So as I said, in you have like gradient, Jacobian, VJPs and JVPs operation that are captured in Python thanks to Jax. And we lower that to this gradient dialect. For example, if we take the grad up, we want to lower this grad up to a backprop up. A backprop up, you can see it as a enzyme called enzyme autodiff. So first we split the quantum nodes. We go through the polygraph. We identify all those quantum nodes. We separate the classical processing and the quantum part. And for the quantum part, we register the quantum gradients with, for example, the parameter shift rule, as I shown you before. Or if you have only access to a simulator, you can use the adjoint differentiation that was also presented before. After creating this backprop up, you will iterate over the primal results. So, for example, if you have a Jacobian, potentially you can have something that is not just a float at the end, but like that is a tensor. So first you iterate over all the results, and for each of those results, potentially there are tensors. We will loop over each entry, and for those entries, we create a cotangent, one hot cotangent, and a backprop up. After that, for the backprop up, we will bufferize this operation. That means that we will allocate the gradients, which are the argument shadows. The primal results are also allocated, but marked as dupe no need. We have another operation that is value in grad, and we don't mark them as dupe no need. But for gradients, that's what we do. After that, the cotangents are copied into the result shadows. Finally, we take these backprop operations and we lower them to the LLVM dialect in MLIR, and we call the enzyme autodiff. There we traverse the Collie we check if there are quantum gradients. If you see quantum gradients, you just register the quantum gradient. So you give the 3 pointers, which one is to the function, one is to the augmented forward pass, which is I think also the same because we didn't change anything in the forward pass, and the last one is a pointer to the custom gradient function. It's a pointer to the parameter shift rule or the adjoint differentiation. After that, we loop over the arguments. We add the necessary metadata, const, no need, and everything that is needed for each pointers. And finally, we call enzyme autodiff. So in conclusion, with PennyLane and Catalyst, you have a nice UI that allows you to prototype fast in Python. And when you need performance, you just have like to decorate your function. Of course, there are still some issues with the integration with enzymes. Sometimes we have unsupported operations that are created, but we're still working on that to make it better. It gives you an integration with machine learning thanks to enzyme, and gives you the ability to move fast and to prototype fast. And also, I think in quantum computing, the bottleneck right now is the hardware, but it prepares you for quantum hardware that is more performant, the quantum hardware of tomorrow. So that's the Catalyst team. There's David, Eric, Ali, Sergey, and myself. So thanks to them for building that software. And also special thanks to Jacob that helped us last year to put all of that together for the enzyme integration. And I'm happy to welcome your questions.
Thank you. Any questions? Jesse?
I'm curious, the ED algorithm you described, how does it compare in terms of efficiency to the primal code?
Can you please repeat the question?
Sorry, I didn't hear. Can you come a bit closer? So which algorithm?
So with some like shift.
Yes, the parameter shift rule?
Yeah,
yes,
yeah.
Okay, so maybe let's
But I guess I'm asking in general, how should I think about, automatic differentiation with some guarantee of efficiency, right? I'm wondering what sort of efficiency guarantees do you get in this context?
So I don't think there is any guarantee of efficiency. This is the only rule that will apply to quantum hardware that is available on quantum hardware that is exact. So you could use, for example, finite differences, but that provides you something that is potentially inexact and that leads to more quantum execution, and we would like to reduce the number of quantum execution. The adjoint differentiation, you cannot apply it on hardware because you don't have access to the state. And that's the big problem there. So parameter shift is the current rule that gives you an exact solution. Maybe there will be more efficient rule discoveries for that, but I think right now that's the best approach.
And then one more quick question. Do you have guarantees of reversibility? Or basically that the programs that you generate in your DSL are realizable on hardware?
Yes, what we do is that when you use, for example, a parameter shift, what will happen is that we have the gradient dialect, and we generate the parameter shift rule in MLIR.
Oh, I guess I'm saying just for the primal code. Is there a guarantee that the primal code is realizable on hardware?
So yes, you don't see it here, but we have a bunch of transforms that we apply depending on the device. Because, for example, if you have a photonic device or a superconducting device, you do not have necessarily access to the same set of instructions. So there is a lot of preprocessing and decomposition of gates. It's not guaranteed that you will be able to run every code if there is not a decomposition rule that will decompose to the needed instruction on your hardware.
Thank you.
Other questions? I actually have one question myself. So we've seen today in the morning and yesterday that there is now presumably enzyme MLAR that
Yes.
works on MLAR. It's very abstract, but now you see you're using enzyme on LLVM and you're
Yes.
presumably having LLVM intrinsics for
Yes.
quantum. Do you think it would be helpful to do AD on a higher level in your case?
Yes, I
or
think
is it moot?
that's something that we would like to do. I think that we were waiting for the MLIR enzyme to be ready for that. And last year, I think the support for the reverse mode was not fully implemented. But once we have something that is like more or less stable, we would be happy to switch, because I don't think we leverage anything in LLVM right now except an enzyme. Yeah.
Okay. Yeah, just more like what would you think would be like why LLVM is not enough? But we can take that offline because I see people are craving coffee. Any last question?
I can move on, thanks.
Okay. Then let's thank the speaker again and
Thank you.
we have a coffee break until 4:10 p.m. so we have enough time for coffee.